question about Physics 6B, video response.
Video response we had for, I think it was a midterm problem for, I think, Physics 6B. Okay. So this is the question actually one of our students, Maria, asked. So I think it's something like this. I think it's something like you have some sort of charge over here, and then you have some sort of charge over here, and they're the same charge, I guess they're both positive. I won't plug in the actual numbers. You can if you want. It's no big deal. I think this is something like 8 meters. And then the question was, what was the strength of the electric field at some point, let's say, 10 meters away? And then at some point, I think the second part was 2 meters away. Okay? Okay, so remember, the idea is if you want to see what an electric field does, you want to imagine that there's a positive 1 Coulomb charge there. Okay? First to get a direction, and then literally what a field is it's force per unit charge. So what that means is it's the amount of force you would feel if a 1 Coulomb charge were there, right? That's also a vector, so it gives you direction. Okay, but for the moment, imagine we put a positive 1 Coulomb charge here, and let's think about what would happen. Well, first, this is a positive guy, so this positive guy as a source charge would push this guy out, right? So this guy would push this guy out like that. Right? And then now look at this guy. This guy too is a positive charge. So he would push this positive guy also out like this. Does everyone agree? And if I call this 1 and this 2, then this is the force or the field generated by 1, and this is the field generated by 2. And everyone can see that if you want to compute it for 10 meters, right, then we would add the two fields together. Okay? And I'm going to take our shortcut. So to compute the field, remember, for a point charge, it's really easy to compute. It's going to be kq over r squared. Okay? So let's plug that in. So k is the constant, right? Q in this case is a source charge. So the q source in this case for field 1 was this guy. So it's just q. Okay? Positive q. And then what about the r? Well, in this case, total distance is 10 to here is 8. So this distance would be 2, right? So if I want to just plug in a number, I can plug in 2. I'll keep it a little more general for the moment. I think in this case, well, it's okay, we can do that. So in this case, it would be 2 squared, right? Okay. If you wanted a more general form for this, this would have been k, q, and in this particular problem, it would have been your distance x, right? Minus this distance here to get you the distance between the two. So in that case, that would have been 8. So x minus 8 quantity squared. But for for plugging in values, you would use this guy. In general, this guy would do it for you. Assuming, of course, you're over on the right-hand side, past the 2. Okay. So now that we got this field either in specific form or general form, that will be the first guy. Just to make this problem fast, can we do it for the second guy? So let's compute E2. E2 is the field here, active at this point here, right? Due to who? Due to this guy. So what I want to do is take his distance. His actual distance is the full 10. So again, it's kq source over r squared. This distance is the full 10, so 10 squared, over k is a constant in front. The q, the source charge here is again just positive q. So it would be this. Okay? If I wanted in general form, this would look like kq over your full x value squared. Okay. Not too bad, right? Okay, so for this solution, for the first part, what is the field over here, 10 meters away? It would be the first guy plus the second guy, which in this case plugging in would be kq over 4 plus k, plugging for the first guy, right? And then for the second guy, plus kq over 100. Okay, so not too bad, right? And everybody agreed they're joining and they're pushing that way. So superposition says, if you want to know the sum effect, just do the first guy, then the second guy, and then add them together. Okay, so no big deal. So we'll send the first part of that away. Now let's do the second part. What would it be if you were only 2 meters to the right of the origin, right? Okay, if that's true, imagine again that you have a small positive 1 Coulomb charge here. Okay? Then think about the effects. This positive would push this positive to the left. So there would be field going in this direction, and it's being generated by, we call this guy number 1, so we'll call this again E1. Okay, so I'm doing a different problem. Now I'm doing the second part that says, what would happen if you wanted the field right here, 2 meters to the right of the origin? Okay? Again, we're going to have the same general strategy, but let's see. And if I were doing this with vectors, actually, because I'm being really sloppy not putting the vector notation, it would still technically be E1 plus E2, but I would have to give it direction. Okay? So if I wanted to be really technical, I can make to the right positive, right? And since E1 is going in the negative direction, I'm going to think that this is a negative guy. So he's negative. Okay? Okay. And then let's keep going. Or you know what? We'll do even more common sense than that. But for the moment, can everybody see this guy is going to the left? So this will be easier. Now, think about what this guy would do. So this guy, we call him number 2. He's positive, he's positive. He's gonna push this guy, not to the left, but to the right. So you see in this setup how they're fighting one another? So this time they're going to work against each other. So if I kept this guy E2 in the positive direction, I can think of this as E2 minus E1. Where E2 and E1 don't have direction built in, they're just the total magnitudes. And then the direction is given by this is positive, and this is negative, telling you it's that way. Okay? So does everybody agree? If I take this difference, I will get the total field at this point. Okay? Again, technically what I'm doing is I'm getting the magnitude. If you really want to be exact on this, the vector notation would literally be E2 plus E1 is equal to E. The reason why there's no minus here is that you would put that negative as a direction inside of this guy. Okay, so this guy would code for both direction and magnitude. So it would actually look like, well, we'll compute it and I'll show you how to change it. Okay. Okay, so let's run with this. By the way, we can even guess the direction. We're going to use common sense. Since both of these charges are the same size, right? Then you know that this guy's closer, he's going to have a stronger push. So I think the final direction is going to be to the right, okay? Which would be positive in our system, or if you're using vector notation, this would be I. Okay, but let's compute this. So E2 would be generated from this guy, right? So this distance here. So this is 0, and this is what? 2 meters, so the distance is 2. So K, Q source, over R squared, right? And then in this case, that would be K, Q source, which is just Q, over the distance here, which would be 2 squared, right? Minus K, this other Q source, happens to actually be the same magnitude, okay? Over this R squared. I'll call this like big R squared. Okay, so K, Q, over. So what about this guy? So let me see. This guy is out 8. This is out 2. So the distance between them is 6. So 6 squared. No big deal. So then, I guess we could finish this up. This is K, Q over 4 minus K, Q over 36. Right? And actually here, if I did it the right way and you compute this correctly, the number you should get is positive. So what that tells you is this is the magnitude, and since it's a positive sign, the direction is positive, which in our system would be to the right. Okay. So hopefully everybody's okay with that. And in fact, what's an easy way to do this? So everything that we did encodes the magnitude. It even actually encodes the direction because of our sign conventions. Okay, and I just wrote this for ease. If you did this in a formal vector equation way, which I don't think you have to, this guy would have been something like KQ over 4, right? And I believe the push was to the right, so this is in the I direction, plus this guy, which is KQ over 36, right? But remember, the push was to the left, so that would be in the I, not the regular I, but negative I direction, right? Which is the same thing. So we're doing this guy minus that guy. The direction is being encoded here. Here we just made it explicit, plus minus that. And that would give our sum vector, which is whatever that is. In fact, we could probably do that. Multiply top and bottom by 9. So this is 9Q minus Q. So I think that's positive 8Q over 36. K is a constant, and I think it turns out to be positive, so this would be our final vector field. Okay? Depending on how formal you want this to be. Okay. Probably, this really wasn't...
Now I get it.